density. Density is a ratio. All right, so it's just a ratio. Ratio of mass to volume. Right, so it's the formula for density is mass over volume, and it's just a ratio. Now, the SI units are kilograms per meter cubed. Now, a cubic meter is a quite large volume. Most humans can fit into a cubic meter and stay alive. So we're not going to use that. We're going to use grams per cubic centimeter or grams per milliliter, just because that's easier for us to work with. We want to note that, I want you to note that 1 centimeter cubed is 1 milliliter. They are the same thing. Okay, and the density of liquid water is 1 gram per centimeter cubed, or 1 gram per milliliter. Now, of course, this is only at 4 degrees Celsius, but we're going to use it unless otherwise told. So the density of water will be 1. It's like 0.999 something. So we'll use 1. All right. So all it is a ratio of mass to volume. All right, and we're going to use it to do some as a conversion, as a for calculations. So now, 2 examples real quick. A certain mineral has a mass 17.8 grams and a volume of 2.35 centimeters cubed. What is the density of this mineral? So we're looking for density. Get my pen back here. D M V. All right, the question is the density. I have 17.8 grams and 2.35 centimeters cubed. So we can just simply do the D equals M over V and solve for this. So the mass, 17.8 grams, and the volume was 2.35 centimeters cubed. All right, and if I do this, I get 7.574468 grams per centimeter cubed. Now, this goes back to the sig figs that we just talked about. Sig figs, how many sig figs are up top here? 3, right? 3 sig figs. On the bottom, 3 sig figs. So my answer can have 3 sig figs. And so my answer is going to be 7.57, right? Because 3 sig figs, since that's a 4, we keep the number, grams per centimeter cubed. So notice we have a number. I have a number and a unit. In this case, it's a compound unit, but it's a unit. So I have a number and a unit, and that's very important. All right, because 7.57 means nothing without the unit. Right? I mean, some of you guys have experienced this with the doctor's office. Maybe you talk to a doctor or nurse, and well, prime example is blood pressure. Blood pressure, 120 over 60 or whatever your blood pressure happens to be. Well, what do those numbers mean? Well, it's actually a pressure. It's 120 millimeters of mercury or torr over 60 millimeters of mercury or torr. It actually has a unit to it. All right. Your blood sugar, maybe your blood sugar is only 60, or your blood sugar is 100, or blood sugar is 110. Well, it's actually 110 milligrams of glucose per deciliter of blood. There are actually units with those, and so but a lot of times we just say the number. We want to always have the number and the unit. Number 2, what's the mass? So there's your question, right? What is the mass? That's our question. We have a 49.6 milliliter sample of a liquid, which has a density of 0.85 grams per milliliter. two ways you can do this. All right, two ways. All right, first way, just like we did above, density equals mass equals volume equals. So we have a mass of 49.6 milliliters, or sorry, we have a volume of 49.6 milliliters. I'm looking for the mass, and the density is 0.85 grams per milliliter. D is M over V. And I'm looking for M here, right? That's what we're looking for. So I can multiply both sides by the volume. So the mass is equal to the density times the volume, right? Multiply both sides by the volume times V, V times, and the volume will cancel. So my mass would equal the density of 0.85 grams per milliliter multiplied by 49.6 milliliters. So my mass would be, looks like it's 42.16, or I have 2 sig figs, right? I only have 2 sig figs for the 0.85, so it'd be 42 grams. And that's my answer. Now, I can use this as a conversion, all right? Okay, I have an amount. So let's point this out. That's an amount, and this is a ratio. And we're going to get, this is going to lead us right into dimensional analysis. So we start with the amount. 49.6 milliliters. And I use my ratio. My ratio, well, milliliters has to go on the bottom. So I put milliliters on the bottom, right? Why? Grams on top. And so this is 0.85 grams per 1 milliliter, right? So this density, right, when I say 0.85 grams per milliliter, it's the same thing as 0.85 grams of liquid per 1 milliliter of liquid. That's the same, whoa, sorry about that. That's the same, come on, same number. It's just more complete. Okay, and we do this math. Milliliters is gone, and we're left with the 42 grams. Same equation, right? But it's just using it as a conversion, which is nice. Okay, because remember, X over X is 1. Milliliters over milliliters is 1, right? They cancel. So that's how we can do that. So this leads us right into dimensional analysis. Conversions. We have to convert units all the time. All right? It's just way it works. All right, and it's a good skill. Look after the units is the advice here, right? A lot of times, if your units are right, you're probably right, unless we transpose the number in the calculator or something. All right. So now, this is where I'd recommend using that sheet that we gave out with the in the original announcement with the constants and equations, just so that you have, you know, those references to look up. Right, so I'm starting off with 14 inches, and I'm going to centimeters. All right, and my conversion is 2.54 centimeters in an inch. It gives us to it. So start off 14 inches. Multiply. What goes on the bottom? Well, it has to be inches, because technically speaking, draw the line, right? That's over 1, right? Because 5 is the same thing as 5 over 1. All right, so 14 inches over 1 is the same thing as 14 inches, right? I'm just dividing by 1, you divide it itself. So inches has to go on the bottom here. That number has to come down here. So I have to have inches down here. And I'm looking for centimeters. All right, and we know there are 2.54 centimeters in 1 inch from our conversion. That's our conversion. I'm looking for centimeters, so I'm happy. So I take my 14 and times it by 2.54. I get 35.56. Now, sig figs. I have 2. This is exact. Right? That's a definition. So it's the exact number. And our goal is to always have all of our conversions either have more significant figures than we start with or be exact numbers and not have to worry about them at all. All right, so I start with my 14. I can only have 2 sig figs here. Since that's a 5, my actual answer becomes 36 centimeters. So it's a rounding. Again, a lot of people don't like to round like that, but I only have 14 inches. Well, you know, think about fish stories. Oh, I caught a fish. How big was it? 14 inches. Maybe if we like bent the ruler, you know what I mean? So there's just, I don't have any data. I only got 2 sig figs, so 36 centimeters is 14 inches. All right, the next one. All right, 8 millimeters cubed to meters cubed. Now I want to point something out here that these are volume to volume, right? But they are linear measurements. Okay, so 8.0 millimeters cubed we know millimeters cubed have to be on the bottom because that way they cancel. Meters cubed on top. And if there's 1,000 millimeters in a meter, let's just do that. And if we do that, I'm going to get 8.0 times 10 to the negative third meters cubed. And that's what I would get if I did that. All right. And the problem is that looks great, except it's wrong. All right, because if you had a meter is, you know, a little over 3 feet, but it's a meter length, width, and height. So it's 1,000 millimeters by 1,000 millimeters by 1,000 millimeters. Length times width times height, which is more than, you know, 1,000 times 1,000 times 1,000. So there's a couple things we can do. First, you can just put parentheses around, and that'll work. If you need to, you can write 1,000 millimeters times 1,000 millimeters times 1,000 millimeters on the bottom by 1 meter by 1 meter by 1 meter on top. That works as well. So that's not our answer. Our actual answer would be 8.0, our 2 sig figs, times 10 to the minus 9th meters cubed. All right, much smaller. All right, much smaller. That's 1,000,000 times smaller. So we've got to make sure when we have linear measurements and we're doing volume, we have to cube them. When we're doing linear measurements for area, we got to square. But if you're doing volume measurements, you don't have to do that. There's no cubing value. So if you're going from like liters to gallons, there's no cubing. Gallons is a volume measurement. Liters is a volume measurement. Liters to milliliters, same thing. There's no cubing because they are volume measurements. But these are linear measurements we're using for volume, so you have to cube. And last example, we're going to do kilometers per hour till meters per second. All right, so we have 60 kilometers per hour. And just so you know, that's 3,600 seconds in an hour, there's 60 seconds in 1 minute and 60 minutes in 1 hour, right? So that means 60 times 60, 6 times 6, 36, 2 zeros, 3,600 seconds in 1 hour, right? That's how many seconds are in an hour. You don't have to do that. You don't have to memorize that. You can do 60 seconds in a minute and 60 minutes in an hour, and that works. All right, so now we have a compound unit, so we have to do both. I'll start with doing the top unit first, and then the time unit second. You don't have to, but I'm going to do it that way. All right, so first up, kilometer on the bottom, and we're going to meters on top. And then there's 1,000 meters in 1 kilometer. And that's it. And then we are going to do hours to seconds. So in 1 hour, hour has to go on top. H hour. Yep, 1 hour. Right? I can put 60 minutes down there or 3,600 seconds down there. Right? The other way to do it would be 1 hour is 60 minutes and 1 minute is 60 seconds. So that could be substituted up there too. If that makes you feel more comfortable, please do that. And if we do this math, I get 16.667 meters per second. Now, how many sig figs do we have? 1 sig fig. So that means my answer is 20 meters per second. Right? I only have 1 sig fig. Right? And that's just, I mean, it's how, it's how it works. Right? It looks like you're losing some, but you're not. Now, if it was 60.0 kilometers per hour, I would make it 16.7 meters per second, right? So it just depends on how accurate our measurement is to begin with, determines how accurate our measurement or how precise our measurement is at the end. All right?